So this is practice problems, mechanisms, answer key. I'm going to start with D because it is the first one that has real math. So you may know that this first thing Dr. Spencer wrote, from the slow step, the rate is K2CE. That comes from up here. These are elementary steps, and so you can write rate laws directly from them. So we say from right here, slow step, we say C times E, both to the power of 1 because they have no coefficients. So C, concentration of C, concentration of E times K2. K2. Okay. But, as written here, C is an intermediate. In other words, it doesn't, we don't start with it, we don't end with it, we really don't know how much we have of C. So we have to do this other math. So we use this rule that in equilibrium, in an equilibrium reaction, the rate from the left to the right, or products to reactants if you wish, is the same as the rate from the right to the left. So in this case we have A and B turning into C and D, and C and D are turning into A and B at the same time. And so you end up with this kind of interesting algebra that you can do. But first let's write the rate laws. So the equation is A plus B goes both ways. Can't draw two arrows on the computer. A plus B turning into C plus D, and the other way too. So if we write the rate law for the left to right, we have A. I should put K. K, let's see. Not just K, K sub 1, because that's written right there for that way, left to right. There's that, and I'm getting that from both of these are coefficient of 1, so you just write it. That's not too hard. And then for the other direction, same rules. So there's K sub negative 1. It doesn't mean you do any math to it, like you don't, it's not the same as K to the power of negative 1. That would be 1 over K, and that's not what it means. No, not this. K sub negative 1, this is just a label. And it means whatever K is for the reaction in reverse. Usually it'll be given, or you just kind of write it and you don't know what the number is, but you just kind of write it. So we have these two rate laws that we've just written down for the same reaction in both directions. And it turns out you can actually set these equal to each other. And this is where the algebra, while easy, is it gives you a slightly more messy expression. By the way, what are we solving for? Let's see. Well, there's an intermediate, and we want to get rid of that. So we solve for that, and then we'll plug it into what we already had. So to solve for C, you divide everything else. Let's see. I'm going to rewrite this just to show the algebra very clearly. I'm going to divide this stuff over there. So that's not too bad. And that's what's written here. She wrote D a little differently, but I think we all know that that's the same thing. If I put to the power of -1 over here. Or if I write it exactly like she did, with a fraction over on the left side. These are all equivalent. So we take our wonderfully short rate law and then we plug in that mess. There it is with the mess plugged in. And then we can combine all the k's together because why not? Makes it easier to write. And we'll call that k over all. And there you have it. You might notice that k over all is, which Dr. Spencer didn't write this, would be all these k's multiplied together. K2 times K1 times K all divided by K -1. There. Which you could write extremely messily as with a negative exponent, but that's just confusing, so let's not do that. Let's just stick with the fraction.